Today, class, we're going to learn about linear motion, which is a basic fundamental of kinematics.
To begin, let's go over some terms. Position is the location based upon a coordinate axis system. Distance is a scalar that represents the total amount traveled by an object. And displacement is the overall change in position of an object. And later you'll learn that displacement is also the integral of velocity. But to help you guys understand a little bit more about distance versus displacement, we have a little picture. So for this red car to go from home to school, the distance and displacement are going to be different values. For the distance is the total amount traveled, so we'll have to follow the car along all the roads. So you'll add all these distances up, and it'll be your distance. On the other hand, displacement is just the total amount of meters, like for here, and meters that he went from beginning to end. So you just go straight and find the distance between home and school. So you just go along this yellow line, and it'll be 800 meters.
Speed versus velocity. It's very important to understand the difference between these two concepts. Speed is a scalar, and it's equal to distance over time in meters per second. It is basically how fast an object is moving. Velocity, on the other hand, is displacement over time, which is also in meters per second. The difference here is that velocity incorporates direction, and it's the rate at which an object changes its position. And it's also the derivative of displacement. The main difference is that speed is a scalar and velocity is not. This is because velocity includes direction, which is the one thing that needs to be remembered. Velocity can be negative.
Acceleration is equal to the change in velocity divided by the change in time and is measured in meters per second squared. An object can accelerate even if its speed is not changing, and this is because acceleration depends on velocity rather than speed. Acceleration is the derivative of velocity and the double derivative of displacement. The acceleration due to gravity, otherwise known as g, is a constant 9.81 meters per second downward for all objects closer to the surface of Earth. Meters per second squared.
Alright, we're about to learn
Kinematic equation number 1.
Here are some examples and the equations that you use to solve them.
So let's start with number 1. Kinematic equation number 1 is V equals V naught plus AT, where V stands for final velocity in meters per second, V naught is initial velocity in meters per second, and A is acceleration in meters per second squared, and T is time in seconds. So here's an example. A hot air balloon rises off the ground with an initial velocity of 8 meters per second. Over a 10-second time interval, the balloon accelerates upwards with an acceleration of 2 meters per second squared. What is the balloon's final velocity? So, before we begin, we know that our initial velocity is 8 meters per second, our time is 10 seconds, and our acceleration is 2 meters per second squared. So now pause the video and try to solve this problem on your own. Alright, for the answer, first we'll use kinematic equation number 1, which is V equals V naught plus AT, and we'll plug in our numbers. So we know our initial velocity is 8, our acceleration is 2, and our time is 10. So plugging in all those numbers and solving it all out, we get our final velocity of 28 meters per second. Yay!
This is kinematic equation number 2. It reads as follows. X is equal, or X final position is equal to X naught initial position plus V naught times time plus 1/2 AT squared, where X and X naught are measured in meters. A is measured in meters per second squared, and time is measured in seconds. So here's an example. A hot air balloonist rising vertically with a constant velocity and magnitude V is equal to 5.4 meters per second releases a sandbag at an instant when the balloon is Y is equal to 50 meters above the ground. After it is released, the sandbag is in free fall. How long does it take the sandbag to hit the ground? So we're going to start by addressing our variables. So we have V naught is equal to 5.4 meters per second. x is equal to 50 meters, x naught is equal to 50 meters. The final position of the beanbag, or the sandbag, is going to be 0, because that's when it's going to hit the ground. And it accelerates towards the Earth at 9.81 meters per second squared downwards, so we're going to make that negative. So pause the video and we'll get back to the answer. Okay, we're back now. So if you didn't use a calculator, then you probably got it wrong. So we'll explain that later. So we're going to start by plugging in the variables that we know, and we're going to end up with a quadratic, which can be solved using your calculator, or here's a nice screenshot of an online tool I used. And as you can see, the time should intersect at 2 different points on the x-axis. One of these is going to be negative and one of these is going to be positive. And you're going to want to choose the positive answer because, as we both know, time can't be negative. So in this case, the final answer would be t is equal to 3.7903 seconds.
Woo! The last kinematic equation is similar to the second kinematic equation, except that it doesn't incorporate time, and it also incorporates velocity. And the equation is v squared equals v naught squared plus 2a change in position, where v is the final velocity and v naught is the initial velocity. Acceleration is a, and x is final position, while x naught is initial position. Here's an example. A ball is thrown into the air with an initial velocity of 22 meters per second. What is the height of the ball at its peak? So here are the variables we have. We have v naught, which is the starting velocity of 22 meters per second. We also have acceleration due to gravity, which is negative 9.81. And the final velocity is 0, because when the ball is at its peak, the velocity will always be 0. And pause the video to work out the answer. Here's the answer. So basically take the variables you have and plug and chug. And at the end you'd be solving for the change in x. And eventually you'll get 24.67 meters as your final answer. Yeah.
Okay, so now we're going to talk about the graphs of our position versus time graph and our velocity versus time graph. So basically these rules go with calculus. So this time graph is the average velocity. And then if you look at a velocity versus time graph, the area under the curve in a velocity versus time graph is the displacement. This is because displacement is the integral of velocity. And then the slope of a velocity versus time graph is the average acceleration, because acceleration is a derivative of velocity, and velocity is a derivative of our displacement. So let's try some problems using what we know.
Example number 1. Here we have a graph where time is on the x-axis and position's on the y-axis. And basically it's a position graph. And so the first question, what is the total displacement? And basically for displacement, we got to remember that it's final position subtracted from the starting position. So from 0 to -2, the displacement will be -2. For the velocity, at 1 second, we need to look at the slope. The slope at 1 second, as you can see, is 3/2 meters per second. And what time interval is the velocity 0? So velocity in the position graph is the slope of the graph at that specific point. So in this interval from 2 to 4, it's a flat line, as well as from 9 to 10 it's flat horizontally. Therefore the velocity is 0. From 2 to 4 seconds and 9 to 10 seconds.
Alright, let's try another example. So this time we're going to look at a time versus velocity. So our first question is, what is the total distance traveled? And just remember the difference between distance and displacement. So since this is just the total distance traveled, you would add up the areas under the curve as your distance / displacement is the integral of velocity. So if you look at this graph, we'll add up the area under the top, which would be 1 plus 2 plus 1, so no, double that, 2 plus 4 plus 2, and add up the bottom of the curve, which is 2 plus 4 plus 2, so it's 8 plus 8, so our total distance traveled would be 16 meters. So on the other hand, our second question, what is the displacement from 0 to 10 seconds? Since displacement is just your initial position to your final position, you would actually subtract the 2, because when from 0 to 10 seconds, you didn't really move. I mean, you didn't move, but you subtract the 2. So our top was 8 and our bottom was 8. So our total displacement was 0 meters.
What's important to understand is that area above the curve for both position and velocity graphs is going to be positive, and area beneath the curve is going to be negative. When you're underneath the x-axis, this region right here is going to be negative when you're talking about displacement. When you're talking about distance, you treat it as both positive because it's a net. I mean, it's not a net, it's a growth, what would you call it, total, I guess? Yeah.
And then our last question is, what is the acceleration at t equals 6 seconds? So just like velocity for position, acceleration is a derivative of velocity, so we would just look at the slope. So at 6 seconds, our slope is 2 over 2, so it's 1 meters per second squared. But it's going downwards, so our acceleration is negative 1 meters per second squared.
Hopefully we have given you enough tools to understand and utilize the fundamentals of kinematics in order to solve problems involving linear motion.
Thanks for watching!